Right. Good morning, everyone. Welcome to day 3 of MobiSys. We're going to be starting our keynote recording now, followed by a live Q&A. During the Q&A part, you can ask questions. You can ask questions during the talk as well, during the pre-recording. And we will have a live Q&A session with the speaker at the ending. So it's my pleasure to introduce Chandra Narayanaswami from IBM. He is currently a distinguished research staff member leading work on supply chains at IBM Research. His work in recent years has focused on core science and technology for several areas of AI-based electronic commerce and supply chains. His earlier works include the Linux Watch, SoulPad, Personal Mobile Hub for medical monitoring applications, a navigation system that was the first to provide geotagged photographs along with route information, and the OpenGL graphics standards libraries. What we're going to talk about today is the IBM Linux Watch, which debuted at Linux World in August 2000, followed by Bluetooth Developer Conference in 2000, CES and CeBIT in 2001, and the project continued through 2004. The watch ushered many technological firsts and significantly pushed the boundary in embedded software and mobile applications. We're at the 20-year anniversary mark, so with that, let us hear Chandra's talk.
Hi, I'm Chandra Narayanaswami. Good morning, good afternoon, or good evening, depending on where you are. I hope you're all safe and healthy amidst the pandemic. And I also hope that you're having a great MobiSys so far. Today, we're going to take a trip down memory lane with IBM's Linux Watch project, which lasted from about 1998 to roughly 2006. I don't have the benefit of seeing you in person in an audience, but I'm sure that many of you are students who were toddlers when this project was undertaken. I wanted to share this story with you all. Okay, the outline for my talk is as follows. I first describe the landscape in the academia and in the product space in the late 1990s. Then I talk about the journey we had with the Linux Watch, why we got started on the project, what we accomplished, and the scientific advances we made. Then I reminisce about what we got correct and also cover areas where we missed. Then I talk a little bit about the mobile enterprise applications that IBM has been building with more recent devices. I conclude with some thoughts about the future of mobile, which I think is still very bright. Now, the 1990s were a great time for research in mobile computing. Two projects come to mind. One of them is the Project Aura from CMU, which was about ubiquitous computing, and the other is MIT Oxygen. So the Project Aura was about task-driven computing, adaptability in mobile and pervasive situations, designing wearable computers for different tasks, and working with disconnected agents and providing wireless networking. The Project Oxygen was about making computation as pervasively available as the air we breathe. It had multiple components, including mobile devices, sensors embedded into the environment, and intelligence baked into the network. There were several other efforts in the University of California, Berkeley, ETH, Columbia, and so on. Overall, these efforts were looking at programmable solutions and context awareness and wireless computing. Now, the products in the late 90s, on the other hand, were mostly fixed function devices, had low resolution displays, and hardly had any wireless connectivity. We're just starting to see some pagers with initial data services, but most of the devices could not be programmed and they could be used only for the purpose for which they were built. This was rather limiting. In about the fall of 1998, IBM initiated a task force on wearables and mobile computing to try and figure out what we need to be doing in that space. We considered various types of devices, such as badges, wallets, keys, eyeglasses, wristwatches, and more. We also simultaneously considered the environments in which the people were going to be using these devices and the likelihood of people having these devices in those environments. So for example, would the device be with the person when they're playing a sport? Would it be there when they're at the office or commute, and so on? There was a lot of debate on what type of device to build. And finally, we settled and agreed that the watch was the one that was most likely going to be with you on most of these occasions. The watch also was chosen because its size would impose severe challenges and force new ways of thinking about the next generation of personal systems. So here are some pictures that got us all started. We asked the question, instead of just showing time, what if watches could show high-resolution images, contacts, email information, and various other applications on a super high-resolution display using very elegant interfaces? And here are some of the members of the team that made it real. The members on this team had diverse skills, ranging from hardware design to operating systems, energy management, display systems, and mechanical packaging, and industrial design. Several more people contributed on the project off and on through the course of the 1998 to 2006 timeframe. This team was extremely talented and worked very closely together. And it's one of the reasons why we were able to achieve so many things with this project. So you would ask, why work on this? And the answer is simply, we wanted to define mobile computing, or the future of mobile computing. And this gave us a great opportunity to explore various areas such as hardware, human-computer interaction, systems and software, and also the applications and services. What if we could provide intuitive, glanceable interfaces and create new user experiences, provide stunning displays, and manage power and provide long battery life, and also include potential wireless communication and include just-in-time information that's delivered to various devices as needed. Soon after the project got started, we asked several people what they would want to see in the WatchPad. And we got back a list that was very long. And that included things like a GPS, a tour assistant, or a coupon wallet. Now, some of these things look obvious and very simple looking back, but in the 90s, the environment was quite different. We're just getting started with some of the wireless communications. The cellular coverage was very poor, and while the internet bubble was ongoing, there was no social media or app ecosystem or the various things that you all are used to. Given the applications we wanted to build, we came up with a set of key requirements, and this included a brilliant high-quality display, wireless connectivity with an intuitive interface, a device that would turn on instantly, and also would look elegant simultaneously. This had many implications in terms of packaging, in terms of what controls to include, in terms of system design, and also how to build this in an overall efficient manner. So some of the key design questions around hardware were processor selection, memory, I/O controls, and so on. And simultaneously, we had to look at the applications in tandem to see what applications would be distilled from the list that we got initially, and also how applications could be synchronized. We also had a huge emphasis on being able to view third-party content, so that became a priority for us as well. So some of the tough questions around the hardware components were seen in the beginning, and I'll focus on a couple of them. So for example, we needed a low power processor given the battery was going to be very small. It needed to operate at multiple frequencies to match the capacity of the tasks that were going to be run on the device. And also the system itself be available as a bare die so that we could attach it to a board that was small enough to fit in the watch. In terms of interaction, We were convinced that there was no room for lots of buttons on the watch, wanted to use a simple finger touch-based model of interaction. But one thing that occurred to us is that the finger would obscure the touchscreen when scrolling. So for this purpose, we added a jog dial or a scroller wheel to allow scrolling without obscuring the display. We also considered rotating bezels and a touch-sensitive watch frame, but since we went ahead with a square watch, the rotating bezels were not pursued. Next came the question of hardware and packaging. Once we had some of the processor and the parts chosen, we had to go find them. And what we learned was that finding these prototypes, finding parts for these prototypes was not that easy. In order to fit all the circuitry that we had in the function, we had to resort to high-density packaging, a board which had 8 layers in all, 6 layers of wiring and 2 layers of power. And we had to have it in a bare die form to be able to fit it. We had to connect the various boards on the system using a ultra-low profile elastomer connector and tighten it with screws on a plastic case. We had to design 2 versions of the watch because we figured that the wireless module would not fit in the smallest watch. Next came the important question of what operating system would run on the device. There were several choices, but we ended up choosing Linux. There were several reasons for this. First and foremost, we're seeing a lot of developers becoming familiar with it, and there was a growing ecosystem around Linux. The other operating systems that were commercial were also hard to license for research projects. Simultaneously, IBM was backing Linux and porting it onto mainframes. So we thought it would be a great story to tell when we said Linux would be running all the way from watches to mainframes. While this may seem like a simple decision in hindsight, it was a pretty controversial decision at that point. Some people's reaction was, "You're running Linux on a watch? You must be crazy," and they wished us luck. Next, we had several considerations around the graphics and user interfaces. We knew that the high-resolution display that we needed to build would come later or take longer, so we needed an interim display to get various parts of the project started. We also needed to simulate various pieces of hardware while the original hardware was being built. Finally, we needed a graphics library because we couldn't be writing directly to the frame buffer. We were thinking of proprietary graphics libraries, but we ran into the same licensing issues as we did for the operating system. On the other hand, X11 was available in source code, and there was an effort called TinyX, which was going in the direction of reducing the code size. We could use the X protocol to run remote applications as well. It seemed pretty crazy, but eventually we chose X11 graphics, and it turned out to be a good decision. We also learned during the course of the user interface work that designing icons for super high resolution displays needed additional creativity because our designers had never seen anything at that resolution before. So once we had all the other decisions sorted out, we needed to be able to package the parts and fit it into a watch case. So this is where it becomes interesting. You probably heard of governments paying $10,000 per toilet seat. So welcome to the $3,000 plastic watch cases and docks. That's what it cost us. In spite of using advanced technologies, we had to spend that much money for each of these cases. For one thing, because we had very low volumes. Modern 3D printers, on the other hand, might do the job for much less today. So once we had all those decisions sorted out and the hardware teams were doing their job, we had to start prototyping the software and the user interface and start bringing up various pieces of operating system on different types of environments. So the first thing was, while the initial rendering looked extremely attractive, we're starting to wonder, can we actually build it? So we started looking at small font in phone books in those times to see how we could read it. And then we looked at some of the X-ray viewers and tried to use that as a way to look at the small fonts and simulate a watch size display. So that's what you're seeing on the top left, where we had a cutout and a film on top to almost simulate a touchscreen on top of a watch display. The next task, once we figured that this was actually readable, was to prototype it and show it on a tiny VGA display. And that's shown on the bottom left, where we're using a laptop to drive the display and a projector. Normally, a projector is going to project on a much larger surface, but in this case, the projector was actually smaller than the primary display. Once we had it working on the tiny VGA display, we had to move to the Cirrus Logic development board, which had a LCD connector and an Ethernet attached. And the LCD that we're going to put on the watch would attach to this board, and we were able to prototype the user interface on this board. Next, in the progression was to move the software to a breadboard, which used the exact same parts as the Linux watch. Throughout the course of the project, we had a software watch simulator. It included a ARM7 instruction simulator, X11 graphics, and some graphics kits. We also had power measurement tools to be able to quantify how much power the various software and applications would consume. So what you have here is a set of displays that we had in the WatchPad specification in March of 1999. As you can see, we have many different applications ranging from email, calendars, private information, to train schedules. We wanted to see them all. And below, we have the rendering on the first organic LED display. So for the first time, on a display the size of a watch, we could read cartoons or read the full article of New York Times. Now, it wasn't smooth sailing all along. Our initial organic LED displays had poor vacuum seals, and they degraded in a matter of less than a week. We're rather disappointed by that, but we figured out a solution, and later on, we were able to fix that. Then came the task of bringing up the wireless stack on the device. This is where our choice of Linux actually helped out. There was another team in IBM that had actually developed the Bluetooth protocol stack on the x86 PCs that were running Linux. So our job was simplified from porting a Bluetooth stack on the PC to a Bluetooth stack on the ARM. And we supported several different profiles. Our experience was that we had one of the earliest versions of the Bluetooth chips and that were not power efficient. We were, in fact, one of the first to publicly demonstrate Bluetooth in December 2000 at the Bluetooth Developers Conference. And we found that interoperability was initially difficult, nowhere as simple as what you have today, where you can pair up your phone with your car with simple relative ease. So we ended up with 5 different versions of the Linux watch, starting with the version in August 2000 and going all the way to October 2002. With each edition of the watch, we added significant capability. The second watch had Bluetooth wireless capability. The next one had the super high resolution, brilliant organic LED display. And then we took a brief break from hardware, and we teamed up with Citizen Watch Company to build a prototype that could be produced in larger volumes. This was followed by transitioning the architecture to a PowerPC-based wristwatch. And this was done in October 2002. So what's in the first LCD watch? I'll highlight a few different things. Had a 86 dot per inch LCD display that infrared communication in the first pass, weighed about 44 grams, and the board, the motherboard, which had 8 layers, was only 27.5 millimeters by 35 millimeters. Obviously, it had to fit in the watch, so it had to be small. In terms of software, we were left with 2 megabytes free for applications after packing in the kernel, the binaries and libraries, and the X11 graphics. It was fairly sufficient for us to get started. The next generation of the watch included the organic LED display and was demonstrated in January of 2001. It had a super brilliant 640 by 480 organic LED display, and it was jointly designed with Imagine Corporation. Now, it had the same motherboard as the LCD watch, didn't have the RF wireless communication, but everything else was quite similar. So what's exactly inside the WatchPad 1.0? Right? On the top left, you see the main board and the wireless boards as well, the Bluetooth and the RF modem. On the right, you see how we packaged it and fit it into the small frames. And on the bottom, you'll see we have a watch that actually looks like a pendant because we wanted to provide the opportunity for people to wear it around their necks if they chose to do so. We also have the cradle that was used to charge the watch and also transfer code between the watch and the PC. The next generation of the watch was jointly designed with Citizen Watch Company. The industrial design and packaging was done by Citizen, and the hardware and software by IBM. We added a few key features to this, which included a 2-axis accelerometer, a fingerprint sensor, and a vibrator for notifications. In terms of the processor, we took the next of the Cirrus Logic processor, moving to 7312. We also had a stem switch instead of a jog dial, like the one that's found in the more modern watches from Apple. The battery was also substantially improved. It was about 5 times the size on the previous watch. We increased the flash memory also to 16 megabytes from 8 to allow us to have more applications. So here, what you see is what's inside the WatchPad 1.5. So if you compare it with the parts in the WatchPad 1.0, you see a little bit more sophistication here, where the boards are not connected by elastomer connectors, but have flexible cables. So we could fold them up and then package it into a watch and also put it on the cradle. The last version of the watch that we made transitioned the processor from the ARM7 to a PowerPC 405. It used the same industrial design and packaging as the WatchPad 1.5, and the hardware and software was done by IBM. We bumped up the size of the memory yet again, and we progressed the operating system to 2.4.17. And we prototyped a whole bunch of software on top of this, including the accelerometer demos and the Bluetooth demos. This version of the watch then morphed into something we call the Personal Mobile Hub. So just out of curiosity, on the 19th anniversary of the first showing of the LCD Linux watch, got the curiosity to pull out the watches from the closet and start firing it up with great trepidation. To our surprise, these watches fired up, and I took the opportunity to compare it with the Apple Watch Series 3 that I was wearing at that time. You can see how the two devices compare in these pictures. The WatchPad 1.5 also fired up, but in this case, we had some damage around the corners of the display on some of the watches. So now I'm going to play a video of the watch booting up in September 2019. Let it cycle through the initial boot sequence. There you see it. And that's X11 graphics firing up. And if you noticed, there are a few pixel drops, but otherwise the display looks quite pristine. There's some damage in the top right corner, but other than that, it seemed to have been preserved quite well, which is almost 20 years old now. And here you have the WatchPad 1.5 with the slightly damaged display corners. Here is Linux coming up on it. Soon it's going to fire up the X clock. And there you have it, time on the watch. Here are a few different views of the watch. And here's a WatchPad 1.5, and we're showing the operation of the stem switch. So if you look at the red wheel at the bottom left, you'll see that controlling the display. And on this watch, the display is actually not damaged. It seems to be fairly pristine condition. So once we have the watches ready, we went on a roadshow, starting with demonstrating it at the Linux World Expo in August of 2000. And we were pleased to see Linus himself show up at our booth to look at the watch, to see how it was running an operating system that bore his name. We then followed up by showing the watch at the Bluetooth Developers Conference in December 2000, where we showed the first publicly demonstrated Bluetooth operation, where we controlled a presentation on a ThinkPad using the watch on our wrist. This was followed by presence at the Consumer Electronics Show in January 2001, where we debuted the organic LED display publicly. We then had several other conferences where we demonstrated it, one of the notable ones being CeBIT in March of 2001. Here we have, for fun, some never before released pictures where we suited up with watches. And on the top right is our night duty, where we had to charge these watches because the battery life on these devices was only a few hours, and we had to charge them to be able to do the demos the next day. On the right is the briefcase with which we had to travel to keep these watches in service. Now, believe it or not, we were able to take these as hand baggage in airlines at that point in time. This was, of course, before 9/11. You won't be able to do that today for sure. So once we had the basic versions of the libraries, the graphics, and the operating system running, we were able to make smooth progress because of our choice of operating system. We were in fairly quick order able to bring up various networking protocols such as PPP, Mobile IPv6, and Session Initiation Protocol, and also some of the security protocols such as IPsec and OpenSSL. We're also able to bring up things like DB2 Every Place as an embedded database, and also message brokering. In fact, we were able to even get a text-to-speech engine and an embedded via voice engine onto the watch. It was a partial function, not the full stack. In terms of applications, we moved on from simple calendar applications to symbiotic displays for GPS in a backpack, mobile web services which would provide mobile payment services to other devices such as kiosks, mobile health monitoring, session initiation protocol to help set up communication between various devices, password vaults and fingerprint authentication, and we also dabbled with safety monitoring for automotives. So now I'm going to talk about some of the scientific or functional advances we made during the course of the project. We'll have 4 different areas around power management, a personal mobile hub, device symbiosis, where different devices leverage their strengths, the mobile and the stationary. The mobile having a lot of personal information, but having drawbacks like battery life or smaller displays, and the stationary having better connectivity or fewer power issues and more storage. We also started looking at mobile devices offering web services, which was a new concept where a mobile device would offer a service to the environment. So the first thing we needed to do was improve the power management of the device. Our initial watch would last only 2 hours on the battery. And while it was a place to start, we had several ways to improve the performance. And the first thing we noticed was that there were several idle processes running on the watch, which were part of the standard Linux operating system, but were not essential on a watch form factor device. So we first removed those carefully, and then we noticed that the processor could not be put in a standby mode because of the periodic Linux timer tick. And we figured, do we need a timer tick on a device like this? And we decided that we could use an event-driven mode in some cases where, for example, you needed to wake up the processor to advance the minute hand or the hour hand. So we could put the processor into a deeper power down state in between these timer ticks. And for longer intervals, we could actually put the processor into a deeper clock suspend mode. All these things improved the battery life quite significantly for us. Now, I also note that the first flight by Wright brothers in 1903 lasted only 12 seconds and covered a distance of 120 feet. So you got to start somewhere. So there are a couple of additional innovations in the WatchPad power management. So one of them was the concept of timer pooling. So the idea here was that if there were timers that are adjustable, that could be called at slightly different times, and the application would indicate a range during which the timer has to be called, we could pool those timers and then allow the processor to go to sleep for longer periods. So with all these improvements, we were able to significantly improve the standby power of the watch. Another area we were able to advance was power-aware graphical user interfaces. Note that the OLED watch had a SRAM per pixel, which meant that the power consumed by this display was proportional to the number of pixels that were lit on the display, or in other words, the content that was being shown on the watch. We used this to prototype different ways of representing time, and to our surprise, the analog representation of the clock actually consumed lesser power than the digital representations for certain fonts. We then set a general framework for making graphically power-aware graphical user interfaces. And this is something that is being adopted in several places with organic LED displays now. The next step in our journey was the Personal Mobile Hub. Based on the PowerPC-based watch, we figured that we had adequate extra power to be able to do various types of analysis on the data and also transcode data between different formats. So we converted the watch to a hub which could be connected easily to other accessories or Bluetooth-based appliances such as glucose monitors. We packaged this into a phone form factor, and by adding tri-band GSM GPRS, added additional memory, and also put a much beefier battery to be able to realize additional functions such as mobile health monitoring. So here we have a personal monitoring architecture where the Personal Mobile Hub has additional software, rule engines, event engines, etc., to process data from the body area network and then relay that to a monitoring center in the server. So here on the right, we have a mobile health monitoring toolkit where a patient's blood pressure readings are taken and analyzed on the Personal Mobile Hub, and information could be sent to a monitoring center for additional medical intervention. Below right, we have a Bluetooth pill monitoring box, which would issue alerts if a patient missed a medication at a certain period in time. So with this, we extended the notion of a watch on a wrist to a Personal Mobile Hub, which would serve as a relay for a body area network. Next, we talk about symbiosis between wearable devices and phones. So as I mentioned earlier, wearables have several advantages. They're always with you and can have a lot of private data, whereas stationary devices such as phones are tethered, but they have no battery limitations and may have a speaker with a higher fidelity. So in this particular example, we are using a SIP protocol where two watches initiate a phone call which would eventually be taken between two stationary phones. And this here allowed various people to use a watch on their hand to initiate a communication on their desktop. So here we're showing device symbiosis between the watches and larger public displays. The key idea is that the larger displays can show content more easily than the smaller displays. So the content from the watch may be shown on the larger displays, but if the larger display is not deemed as fully secure or private, the content may be obscured. We blur out some of the sensitive information, and that information is shown just on the watch. Next, we show web services on mobile devices. This was the first time where a mobile device would offer a web service to other devices around it. So in this example, the watch has a wallet web service where it stores multiple payment methods, and a user who wants to complete a transaction at a kiosk logs into the kiosk, and upon logging in, the kiosk asks for some of the payment methods, and the user may submit them, and the payment methods show up on the kiosk. The user may select one of those payment methods and indicate a yes or no to confirm payment on the watch using a fingerprint sensor on the watch. Here we're showing the password vault function on the watch, where we were storing multiple passwords for websites and automatically providing those upon visiting websites in the future, a notion that's supported by many password vaults on mobile devices these days. On the right, we had a novel interface mechanism that we were playing with. The idea here was that a string could be used to navigate the wristwatch to make it even more elegant. The content on the main display would correspond to some of the content on the string. The idea was the string would indicate the number of messages, and the message itself would be shown on the main display of the watch. The angle at which the string was pulled could further modulate the contents of the display and show different things depending on whether it was at 0 degrees or 90 degrees. We then also contemplated flexible displays because we started seeing them, at least in publications. So we started looking at that. And on the left, we have a conceptual mock-up where we have a flexible display that's telescoping on a mobile PDA. And the idea here is that as the display becomes larger, more content or more details of the appointment show up. On the right-hand side, you have a two-sided flexible display where one side shows a crossword puzzle, and on the other side, you have the solution to the puzzle itself. Okay, so here we're showing driver safety monitoring by analyzing the data received from the two-axis accelerometer on the watch. As shown in the bottom sequence of images, when the driver takes their hand off the steering wheel, the readings are sent to the analysis unit, which detects that the hand is off the wheel and then issues a notification. And the driver is able to correct their driving behavior as a result of this. Now let's look at some of the interfaces in the market for devices that we can buy today. On the top, we have the Apple Series 3 watch. It sports a touch-sensitive display and a digital crown, very similar to the interface paradigm we had for the WatchPad 1.5 and the WatchPad 1.0. On the below left, we have the Samsung Gear S3 watch, which uses a bezel to control its interface. It's very similar to the bezel we were contemplating when we were initially designing the watch. The Fossil Q Control watch also uses the circular paradigm to navigate between various functions on the watch itself. So now let's take a step back and look at some of the things we appear to have got right. The first thing I would point out is the adoption of Linux for mobile and embedded devices. Roughly 80% or more of mobile and embedded devices today run something derived from Linux. If you look at the user interfaces on modern phones and watches, all of them support stunning high-resolution displays, use a finger-only touch interaction, use a jog dial or a digital crown or a bezel for interaction, and support fingerprint-based login. Many of these features were first featured on the Linux watch. The need to focus on standby current and have specific processors with various tasks and power-aware graphical user interfaces is also gaining more attention in modern devices. In terms of some of the application domains we chose, mobile health, payments, password vaults, and some enterprise applications were spot on in terms of potential areas for impact for mobile devices. And in terms of device symbiosis, the experience you have with Apple CarPlay and Android Auto are some good examples where you're able to leverage the capabilities of your phone with the capabilities of your car, demonstrating ideal symbiosis. So now, on to some things we either missed or overestimated. The explosion of social media and data gathering was something that we had not anticipated. The fact that customers would view their data so laxly and share them with various parties without a concern for privacy was also stunning. And the fact that a lot of this data would be exploited by various parties without obtaining clear permissions is also somewhat of a surprise. The frantic pace and the proliferation of applications and the lack of paid versions was also not something we thought would happen. The resurgence of AI and the confluence of that with mobile devices was also post-dating the work on our Linux watch. The resurgence of AI happened past 2006 when we had almost wound up the work on the Linux watch. The fact that many of the modern devices, such as watches and phones, have sealed batteries was also something we thought would not happen because we felt that rechargeable batteries were always more sustainable and also more user-friendly. We, in 2005, dabbled with flexible displays, as we discussed earlier, but there is no viable flexible display on the market yet. So there, we certainly overestimated how quickly flexible displays would arrive. So now I want to cover some of the applications that IBM has built on some of the more modern Apple-based devices. We have about 280 different industry applications covering 65 different types of professionals distributed across 16 industries. So for example, in the airlines, we have several applications, field services, emergency services, insurance, etc. And in each of these cases, there has been evidence that we are able to increase revenues, reduce downtimes, improve the speed at which things are done, or the convenience with which things are done. These are all music to the ears of mobile computing researchers who've been working on this vision for a long time. Here are a couple of examples of IBM enterprise mobile applications. The first one on the left is a claims adjustment application for an insurance adjuster who's able to adjust a claim on site without having to go back to the office. On the top right is a passenger application for an airline booking agent who's able to rebook passengers the moment they receive notification that a particular flight has been canceled. And on the bottom, there's an application for managing turn of aircraft for personnel on the ground. So when an aircraft reaches a particular airport, it's able to head back out as quickly as possible, maximizing the revenues for the airline. So what is in the future? Well, I don't have a crystal ball, but I would say that many of the drivers for the future of mobile computing include IoT, sensors, AI and optimization, data and cloud, blockchain, 5G, and also perhaps quantum. So the fusion of AI and mobile is already underway. Fusion of blockchain plus optimization plus mobile could be interesting. And for example, what if a drone could reach out to a quantum computer to optimize its flight path while on its journey? So these are all possibilities over time. We think game-changing applications are possible in various industries, such as healthcare, maintenance and repair, the use of augmented reality, drones, and robots as a wide open set of things where researchers can work and products can be built. There's a lot of room for creating new sensors, for example, for smell, for taste, etc. I also think that privacy-preserving artificial intelligence is going to take further importance as more and more data, a lot of it is personal, is gathered from these mobile devices and personal sensors. I want to end with a thought around the need for sustainable and responsible designs, given that each of us now has several tens of devices that we own. The need for biodegradable or organic electronics is going to be further seen or felt over time because we can't keep accumulating more and more devices without a quick way to recycle them or dispose them off. We'll end with a few projects at IBM that pertain to mobile computing. The first of them is the IBM Crypto Anchor Verifier. Here, a high-resolution camera is attached to a smartphone to be able to observe the spectral properties and color distribution of fluids, look at the patterns on minerals and metals, identify biological cells and count them, and also identify skin tissue damage. So these can be used to figure out whether a product is genuine or counterfeit, or whether a product has been adulterated and contaminated. Another example is secure RFID chips, which are able to sense information around them and encrypt them and send them off into a blockchain. So we think these type of sensors can be embedded in high-value assets and can be used to have supply chain integrity and also track the provenance of the objects, figure out whether they're originals or counterfeits, and identify where they have traveled through in a supply chain and whether they're genuine parts or counterfeits. Here are a couple of examples of sensors. One of them is HyperTaste, essentially using a miniaturized sensor package and artificial intelligence deployed in the cloud to identify the taste of a particular fluid. Another related sensor is called Cogniscent. It integrates custom sensors and various machine learning techniques and identifies highly complex gas mixtures, which can be used with potential applications in food, human health, and chemistry. And finally, here's a sensor. It's called a fingernail sensor, which can be used to figure out various types of activities that a person is doing and progress of cardiovascular or neurological diseases. So for example, here, we are able to identify whether a person is opening a door, screwing a nut, or lifting a can. So with that, I want to thank you and hope to see you in the question session at the end of my talk. Thank you very much.
Right. Thank you, Chandra. I see you're off mute as well. That's wonderful. So to the audience, please use the Q&A box that you see in Zoom to ask questions for Chandra. I will ask them to him on your behalf, and we can see the discussion with a few questions I had for you. So this idea for the Linux watch project is very interesting. How did it come about?
Iqbal, thank you. So around that time, IBM was leading in the PC business with mobile ThinkPads and had top-of-the-line personal computers. And IBM's research's role has always been to help our product groups in addition to advancing science and technology. So we were already packaged the ThinkPad into a vision pad or a personal form factor device like a PDA size. So we're looking at what else could we build that would kind of change the future of computing, what could be a companion device to a laptop. And in those days, if you recall, a laptop would take about a couple of minutes to fire up and show the first screen. And we wanted to see if, while the ThinkPad was closed, whether we could have some useful information pop up on a wearable or glanceable display. So that was one of the motivations in addition to what I mentioned already in the talk.
I see. Very interesting. Another question I had was, this project had elements of industrial design, software wizardry, hardware hacking. IBM Research is a large organization with people, diverse talents and so on. But I still wonder, how did you recruit the team? Did you have difficulty recruiting people for this?
Yes and no to some extent. So let me kind of clarify that, right? So the task force was a fairly high-level task force. So it reached various VPs of different organizations. So they volunteered some of their best people. So for example, we got the people who had worked on the ThinkPad power management, who had worked on miniaturization, who had taken the ThinkPad form factor into the smaller portable PDA size. So we got some of the best people from there and with the displays, and we had some of the industrial designers who worked on the ThinkPad work on the watch. Now, we did have some difficulty in recruiting in some areas because people thought we were too ambitious and we were definitely going to fail, and they didn't want to join a project which they thought might be so risky. So by some coincidence, a lot of the people who worked on the watch were risk takers. And that certainly helped us because everyone was ambitious. They worked very hard and ingeniously to get all this done.
It's amazing. Now, this choice to put Linux as the operating system, I'm thinking back to that time frame. Linux was not as pervasive as it is today. Certainly, there were other real-time operating systems. You mentioned VxWorks. I remember working on that at Motorola around that time on base stations and so on. So what was the key benefits for choosing Linux?
Looking back, I think one of the most important decisions in that project was choosing Linux. So what happened as a result of making that decision was that after we had Linux running and the basic graphics libraries and so on, we were very quickly able to port a variety of stacks that were available in the open source, such as IPsec, OpenSSL, Mobile IPv6. And it was like a geometric progression. If we had chosen something else, I'm sure it would have just been a special gadget, which would not have had the expansive set of applications that we were able to put later.
That's very interesting. As I was doing research for the project, I saw some ideas for watch computers as early as in the 80s, and some of them did not even have an operating system. They were very bespoke devices, not necessarily easy to expand with new kinds of computer programs and so on. So the choice of Linux really lets you access all of the creativity in the world in open source. That's really wonderful. We'll go over to some audience questions. So here's a question from Karthik Dantu. Thank you very much for the talk. It must have been very exciting to work on such an impactful project. I remember following the work on Linux ported to the Palm Pilot, which also had some of the mobile embedded motivations of the WatchPad. Did you folks have a collaboration and or discussions on Linux modifications common to the two platforms?
The Palm Pilot, if I recall, was running a Motorola 68K processor. So while we did keep track of various Linux distributions, we're focusing more on the ARM distribution and looking at where that was at.
I see. So maybe a follow-up on that one I had is one of the later versions also was on PowerPC. And I know IBM, Motorola, and Apple, they were sort of the stalwarts supporting PowerPC. What was the motivation? Why did you pick ARM originally? And then what was the motivation for the PowerPC version?
For the power footprint that we needed and the power consumption at the time we started the project, the ARM was the most viable processor. And as we kind of made progress through it, the PowerPC roadmap was also converging towards going in the lower power direction. And also, as you probably recall, the PowerPC powered some of the gaming machines at the high end, right. The gaming trifecta, if you call it, the Xbox and the PlayStation and so on. And it was going towards the more embedded direction. And that's why we were kind of looking at a PowerPC-based watch as well.
I see. I had a GameCube, which had a PowerPC.
Wonderful.
Right. Yeah. Okay, go for another audience question. This one is from Robin Kravitz from University of Illinois. Thank you for a wonderful overview of the great research you have done. given that you were working on watches way before they were even feasible, and when people thought you were just a little crazy to try to build what you did, were there any wild ideas, applications, uses that you had that have been yet designed into current day smartwatches?
That have not yet been. I think one of them is the resolution of the display we had. It's 741 dots per inch. And if I recall correctly, the latest smartwatches have only about 300 to 350 dots per inch. So it's a little stunning to us that 20 years later, the display resolution is what it is compared to what we had. Maybe 350 DPI is sufficient or plenty, and maybe that's a motivation, but clearly that's something that is still surprising.
Cool. Another audience question. This one is from David Coates. Impressive work, great talk. You describe it in largely linear fashion as the project evolved. But what were some of the surprises, the setbacks, the necessary redesigns? Every large project experiences these moments, and they offer the best opportunities to learn. Thanks.
Yeah, so I think there were lots of different snafus and challenges that came about, but most of them were fortunately in the software side. We're very fortunate to kind of have some of the best designers on the hardware, verify it, and so on. And one of the issues we had, I mentioned briefly in the talk, was the organic LED displays. We were very concerned about whether we'd be able to seal it correctly so that it would kind of retain its quality. And in our initial displays actually lasted less than a week. Maybe one of them died in a couple of days. So we lucked out in some of those areas by kind of paying extra attention to the hardware side of things. On the software, of course, as we all know, we have a lot of chances. It's not like one-shot type of thing, and it's inexpensive. And that's, again, where we could go look at some of the Linux distributions, get together, talk about things. And some of the things that happened were fairly low-level things like double word stores instead of byte stores, and byte order reversals, things like that, that we had to kind of go look at the very low level and then be able to fix it. But again, the choice of Linux made it easier to kind of get some of the remaining things up and running after the initial difficulties we had in getting going.
David was talking about redesigns. I recall from your talk, you had this dental X-ray slide viewer, which I thought was very interesting. So you did a lot of mock-ups as you were going through the process of ideation?
Right. Yeah, in fact, actually, I have that unit here with me. And there, if you can see it, that's the X-ray viewer. And we got this idea, I think I don't quite recall, maybe there was a visit to the dentist or somebody in the lab was having some of these things already. So we said, hey, this is a great thing if we can kind of use this to simulate a watch. And what we had was the film on top to kind of simulate the degradation due to a touch screen. And so that kind of got us started saying, okay, we created something in the graphics visualization, but how does it look in real life? So that was one of the first steps after creating that first visualization.
Yeah, I thought this was very fascinating. You know, when you can do these mock-ups to test out specific ideas, it lets you iterate, and again, at a much lower cost than trying to build the whole thing in one shot, which is of course impossible. Another, you know, in terms of, you mentioned in your talk setbacks, the case that cost you $3,000. I have an interesting story. When I was an IBM intern back 2006, 2008, we had this project where we tried to build a case for an accelerometer, and that came in at $5,000.
Yeah, no, it was quite surprising because you know, you could go buy a Rolex watch for $1,000 or $2,000, etc. And it was stunning that this would cost $5,000 or $3,000 at that time. It was a lot of money in those days.
Yeah, it's quite amazing how tooling has improved. This is on the software side, and more recently on the hardware side as well, where things like Arduino, Raspberry Pi, hardware hacking has basically become you know, much more accessible to students and so on. Another question I had related to this is, back in those days, again, these were early days for the internet. You didn't have all of this content on YouTube. You didn't have Kickstarter. You know, how do you think things are today for someone to approach a project like this? I mean, things are much easier, surely, right?
Oh yeah, things are much easier, but you don't get credit for kind of building what's already there, right? So I think you need to set your bar much higher. Now that you have all this stuff built and ready for you, what are some compelling and interesting applications you can think of and dream up, right? So that's where, and then obviously, as I mentioned, there's going to be wonderful new sensors that we haven't even conceived that are going to sense the environment and provide a lot more functionality and make things more efficient for us.
Right. We'll go to another audience question from Jiming Hu. Thanks for the very interesting talk. Can you share some stories in the business side? Did you consider shipping the product to end consumers at that time?
We didn't get quite that far. I mean, basically, our third version with the jointly done with Citizen, the idea was to get some more watches in hand and be able to develop it further. And that's where at some point around that, IBM decided to get out of the PC business. And that essentially was the place where we decided we were onto something else.
I see. I'm kind of remembering back to the 2006 period, which is when I think the Linux Watch project had largely wrapped up. But at IBM Research, there were a bunch of follow-on projects in pervasive computing and other areas. I know you mentioned SoulPad is one of the projects. I actually recall being at MobiSys in 2005, I think. I think that paper got best paper, right?
Yeah, that is correct. Yes. Yeah. So a couple of things, right? So there was actually a PDA that one of our engineering divisions called Engineering Technology Services that was based in Rochester, Minnesota, working with some of the medical device companies. So there are a couple of directions they pursued it. One was a PDA jointly developed with a company called CDL Corporation. And then there was the Personal Mobile Hub, which was also built using the PowerPC processor itself. So those were some steps in the broader direction.
I see. So my recollection of SoulPad, I remember as a grad student in the audience, I was just mesmerized. The idea was wherever you go, your computing is with you. And I mean, these were ideas you had in this Linux Watch project as well. And it's really fascinating that today we have phones, we have watches, wearables, we have smart headphones. Computing is truly getting very pervasive.
Right. Now, in the, yeah, certainly, I guess the world is quite different. But meaning I do have a few props from the time when we were working on the Linux Watch, if you want me. Let me kind of show you a few things, right? So here is my cell phone, if you guys can see it. This was my cell phone, basically a 4-line screen, right? And this was my second cell phone during the course of the project, right? And meaning much later, even in the 2005 timeframe, this flip phone was what we had, right? Now, during the course of the Linux Watch project, we had a few devices that we were looking at. So I had these in the slide. So this was a PageWriter 2000. This was a fresh new device that came out in late 99 or 2000. And this was the device to have at that point in time. Then came the first version of the Research in Motion device. This was a pager with a 4-line display, but it could get messages. And it was like beyond what a old pager could do, and so directly getting some of your email. So that was a game changer at that point in time, right? Yeah, so we did have a couple of watches to look at as well, right? So we kind of were gadget freaks, so we would kind of go get any gadget we could procure. And these are some of the touch. One of them is the Timex Beep watch, which would kind of use optical communication to receive messages. And this was a Casio touch watch. Didn't do much, but at least had for a few places to incorporate. And the biggest, there are a couple of other devices I wanted to show you. So this is a Psion PDA, and this was running the Symbian operating system. So this was what business travelers or people would carry. And then there was one device I remember seeing in Marty's talk. with the original phone. And here is a phone, it's called the Nokia Communicator. And this is basically how big it was, right? So that was the environment then, and we just wanted to kind of see how to progress that.
That's really fascinating. In 2000, 2001, I just finished undergrad, and I was working as an engineer at Motorola. We would all have those clamshell pagers. It was a hazard when you're done with work, going to your car. People are driving all over the place with their clamshells. I remember.
Yeah.
Another thing I remember is back, again, before the smartphone in its current form factor, there was just this belief that you had to have a physical, QWERTY keyboard on these things for them to be useful for business use. I remember early, even the Windows mobile devices from Microsoft, they would have styluses, they would have these physical keyboards. At any point in the Linux Watch project, did you guys think about, a keyboard in there, or maybe a separate keyboard attachment for this thing that could go in your pocket?
We certainly didn't think a stylus was a sensible idea, given the size of the watch. And we also were sure that you would lose the stylus very quickly, and that was not a right option, right? And we looked at a lot of watches, and many of them had clunky buttons and user manuals, which you really needed those to be able to operate the watch. If you didn't operate it for a couple of days, you forgot. And so we wanted the user interface to be totally intuitive, a graphical user interface, and a touch-operated device with just very simple finger touch based things. Did we think of a keyboard? As we went into the Personal Mobile Hub, maybe we thought of a wireless keyboard that could be part of the dock or something like that, like a keyboard attached thing where the Personal Mobile Hub would sit, but certainly not for the watch.
I see. Cool.
We did port some type of speech engine and a voice engine into it, though not the whole stack. We're fairly sure at some point those interfaces would be reasonable.
I see. Cool. Another audience question from Victor Erdelli. If you were to build a watch today, what would you do differently compared to commercial smartwatches available on the market?
That's a tough question, but I'm a little still surprised that the watch band is not being used as effectively as it could be. There is additional real estate because way back in '99, when we were looking at it, we were saying there's a lot of room there, including putting potential displays, battery, other devices there. And for whatever reason, aesthetics or something, or maybe for safety, it's not been done, but that's something I would strongly consider.
Actually, that's very fascinating you mentioned this, because so you talked about one of the misses that you gave yourself was the fact that you didn't force, or you thought that flexible screens would be a lot more pervasive. I mean, I have to tell you, Samsung, we've got these folding phones, so they're coming.
Yeah, no, I think it's been a little slower. That's what I meant in terms of adoption, but I think they're
just happening now.
Yeah, a lot of potential. Yeah.
Another interesting technology that's actually, there are two pieces of technology that go into your comment about not using the band. First of all, flexible PCBs. So the technology for flexible PCBs is really developing, and I think there are some devices that are starting to use flexible PCBs where you can integrate them into the strap. And another point is flexible batteries. That's another really fascinating topic. I ended up writing an article for Get Mobile, the magazine, where we were looking at various kinds of bendable batteries. And it was interesting that the company that made the bendable battery, they were looking for, again, the first application. And they came up with a very clever application, which was basically a temperature thermometer that you can throw away. Not great for sustainability, but if you're a parent, you're worried your kid has a fever at night, what you do today is check their temperature. And here you just put this flexible Band-Aid on top. And that's a device that's out there. It's amazing where technology has come today.
Yeah, absolutely. I was at a medical devices conference, and that's where I was seeing some of these flexible patches and things like that, because they need to conform to the skin.
Right.
Yeah.
Okay, another audience question from, sorry if I mess up your name, Mukulika, thanks for the great talk. Was the watch interfaced with the mobile phone? What type of phones were supported? Also, what different sensors were there and how were they used in terms of applications?
At the time we kind of developed the watch, there were no smartphones to really connect to with ease. So that's why we built the Personal Mobile Hub and connected the watch to various other devices, such as SIP-enabled PDAs and various PCs and so on. In terms of the interface, the sensors, we had the accelerometer. So we used that for safety monitoring, for driving. We used it for positioning and rotating information, used it as a remote controller for a presentation on a laptop. And so those were the types of things we were able to do with that. We had the fingerprint sensor for authentication as well.
I thought that was, again, very, very prescient. You look at modern mobile devices with, trusted execution environments starting to become more and more used. And it's amazing. There were talks at MobiSys as well that covered this topic. So yeah, there are a lot of questions here. Here's one from Marco. Amazing work, great talk. Imagine you were to embark on a similarly ambitious next generation device project today. How has the research environment changed? Would you make such a project? Would that make such a project easier? What would make a similarly ambitious project harder?
So let me give you an example, right? Maybe not directly answer the question, but I've gotten into gardening these days. And some of my routine includes walking around the house, first actually checking the weather forecast, walking around the yard, looking at which plants need to be watered, and then go water them, right? So now if you look at all the tools that are available today, meaning at that point, 20 years ago, Linux and the libraries were the big thing. Whereas today you have artificial intelligence libraries, machine learning, vision, all these type of things, ability to kind of capture satellite information, drones. So what I would like is, for example, a coordinated set of devices, mobile and pervasive, which would probably automate my tasks. So for example, a drone goes around my yard, does all the inspection, figures out which plants need to be watered, identify the plants using imagery, figure out their watering frequency, etc. And then commission a robot to go water them, carry the pipe, etc. So that would call for a lot of different types of coordination, robotics, drones that can coordinate, and artificial intelligence, some of that in real time, right? And also bringing in real-time weather forecasts. And so I think we're at a point where we are able to do a lot of things inside our home. It may be also possible to do a lot of these things outside of our homes. Some of these things in pockets are happening with respect to inspection in utility companies and so on with drones and things like that. But I think there's a lot of new things that can be done.
Right. But in terms of the research environment itself, like in terms of maybe, is there more pressure to publish today, for example? What are your thoughts on that? I think every generation kind of talks about how, there's so much more the publish or perish. Was that sort of similar back in the days of your project, or do you see that different?
I don't think anything has fundamentally changed. The process of publications or publishing has become a lot more democratic. I think there's other avenues. I remember there were only a couple of conferences in those days to publish, and they were publishing only 20 or 20 odd papers, right? Where even if you take a conference like NeurIPS, which was called NIPS at that point, there are just a few tens of papers. The latest editions have several hundred, right? So, and also, obviously, as we kind of make progress in this area, we need to come up with more and more interesting things. So I don't think anything has changed fundamentally. It's just a general progression of how we can use earlier technology.
That's actually a very fascinating point. One of the first papers I think you had on the project was published at ISWIC. Is that right?
Correct. Yes.
So it's interesting because ISWIC was fairly young at that time. I think the first iteration was only 97. So some of those conferences were new, and it's really exciting that when you're working on a new topic, perhaps it's a workshop, and that's when things are coming up and the new ideas are being discussed. That's
absolutely. That was a fascinating conference, and the demo sessions there were absolutely very thrilling.
Right. Okay, I'm going to take one more audience question. You talked about some newer applications around mobile enterprise that IBM's built for various different kinds of businesses. So the question is, I guess the size of the IBM engineering team that works on this. I think you said there were 15,000 iOS engineers.
Yeah, 15,000 developers overall, all across various parts of
I
IBM.
see.
Yeah.
And then sort of, yeah, there are questions about revenue and so on. So I guess this is a pretty big deal for IBM in terms of this whole enterprise mobile applications.
Yeah, there's a whole set of people working on it, and I don't have the revenue numbers or whatever, but certainly it's an area of importance, and given by the size of the
Right.
teams there.
There was actually a related question where the person asks, despite all the sensors, computing power in the smartwatch today, they're not being widely used for mobile health. I'm assuming this is beyond just fitness. This is actually used by medical professionals like doctors and so on. Do you have any thoughts on this and where this is headed? I think it's an interesting question.
Yeah, so meaning I think while these devices are capable and so on, the rest of the ecosystem has to be there. So for example, easily accessible electronic health records with the proper access controls, automatically figuring many of these things out. So I think there's a lot of room for AI to help with those type of things and make those tasks happen more automatically. Then I think there would be more adoption of these technologies. It's an end-to-end system. It's not just one piece here that drives the whole thing.
Okay, I'm going to ask one last question. We're a little over time as well, but I think this was a very fascinating question from a member of the audience, an anonymous attendee. Thank you for the talk. Very cool work. What general advice would you give to someone looking to create a hardware prototype, both in the context of a large company like IBM or as a solo contributor? I know hardware is really hard, so really looking forward to your answer here.
Yeah, so meaning obviously depends on your goal. If you want to kind of produce something very quickly, which has some immediate application, meaning it's perfectly fine to take the existing Raspberry Pi platforms and the various off-the-shelf parts. Now, if you want something that's super ambitious, depending on your project goals, then you need to start having a design, figuring out things, having control at the right levels so you're able to change things. So for example, in our display, we were able to control the power because that's how we designed it. If you just buy something off the shelf, you're going to be limited. So it obviously depends on how far out you're shooting and how ambitious you are and what your goals are.
All right, cool. Thank you. So we're already 10 minutes over time. We'll have to end this. Thank you for the wonderful discussion, wonderful trip down memory lane. Thank you, Chandra, again. Thank you to the audience for posing very interesting questions. And we'll see you at the next session. Take care. Bye-bye.
Thank you very much for having me. Okay, bye now.